Hi everyone, I'm Bûn-Kim. I'm going to present you the work that I'm doing for my thesis on prevision of weather phenomenon for aviation under the supervision of Alvaro Moreno, Javi Garza, and Manuel Soler. We are going to focus on atmospheric wind shear for this talk. So what is atmospheric wind shear? We can define this as a variation in wind speed or in direction of the wind on the confined space. And when it happens, sometimes we can see some nice cloud formation, like lenticular clouds and Kelvin-Helmholtz clouds instability. And wind shear is like a 3D vector. So each component of the wind shear will have like a different effect on the aircraft. So here I just showed two components of the wind shear, and can lead to like a sudden loss of the airspeed, and altitude can a loss of altitude can occur. Many airports are concerned by frequent wind shear phenomenon. For example, those who are like near the sea or near mountains. So if you are in both cases, it's very frequent. For example, this one, I took this one like in New Zealand. The airport is like located on the Blue Star. It is near the sea, so you often have like some wind coming from the sea, called some breeze. And because it's near the mountain, you often have like a very perturbed flow because of the obstacle, and your flow is very chaotic. And between both, you often have like a conflict area. And if your port is between both, it's very unfortunate, and it can be very dangerous sometimes for aircraft. And for example, here it's on this airport. It's a video of an aircraft who tried to land and struggled because of the very high wind shear phenomenon on this day. To prevent all this, aircraft rely on what they call predictive wind shear warning. This is a system which is mainly based on Doppler radar, like inside the aircraft. And the idea is that to use the radar to detect wind shear area and then send a warning to other aircraft. One critique that we can have on this is more detection than prediction. So it's a very short warning. And it has like the limitation of the Doppler radar. So it is mostly working when the atmosphere is humid, so when it's rainy, and very sensitive to ground echoes. So it's a bit annoying when you want to predict low-level wind shear. Concerning machine learning and weather models, there is many works, so I cannot do like a full state of the art. But if I just focus on 2 years, 2022 and 2023, which were very important year for development of weather models and AI, there is many actors who launch the model, private actors and public academia, as always, like Huawei, Google, NVIDIA, Microsoft, and lots of academies. And these models were very competitive with very classic models. So it was a bit a breakthrough for that. And one critique that we can have on these models is that they are all data-driven. So sometimes the physics is a bit not well respected on these models. The goal of my thesis is to develop a product to anticipate wind shear phenomena. And we want like around like a 1 hour forecast at a 10-minute spatial resolution around the airport at a kilometric resolution. So for the moment, for the temporal resolution, we are on these waters. But for the spatial location, we are struggling a bit to reconstruct the winds at very low level of the atmosphere. And I'm going to present you all the work like for like upper part of the atmosphere. The strategy that I adopted for this challenge is in two parts. Like the first part is to use available data, such as observations like satellites, radar, aircraft, and weather stations, that I'm combining with other sources of data like weather models and weather parameterization to go from sparse observations to a full field. So this is my first model. So this is the AI reconstruction. And the second block is the AI prediction, where I take as an input my full field and try to predict the next state of the atmosphere. So it's very in two blocks. I'm going to present you the first block. The first block, as I said, is going from observations to like a full field of the atmosphere. We are going to use for that physics-informed AI. It is some AI that we bridge with some physics knowledge that we have. In this case, the system is the atmosphere. So our knowledges are mainly the Navier-Stokes equations, like continuity equation, momentum equation, the hydrostatic equation, and others, like the thermodynamic equation, water equation, and whatever we have. To set my experiment, I will show you like some results where I only assimilate satellite observation and aircraft observations. For satellite, I'm going to use a product called atmospheric motion vectors. It is wind observation that we are deriving by tracking the clouds through several images. And for the aircraft observations, it's in situ observations. So it's very like you have your aircraft and the aircraft have some probes and can measure the state of the atmosphere at the location. And we are going to compare our result with the ERA 5 reanalysis, which is often considered as a very, very good quality data set to know the state of the atmosphere. For the situation, it is the state of the atmosphere over Europe for the 1st January of 2023. It was a very extreme event because we were in winter and it was like 20-25 degrees with a very specific weather situation. We can see on the left that Europe was concerned by a very high intensity jets with very strong wind for the U and V components. For the U components, there was a very strong intensity near the North Sea, and the V component was more concerned by strong adduction coming from the Atlantic. And for the reconstruction that we have from our satellite and aircraft observation, we are mainly able to capture this high intensity jet that was located over Europe. I put it on the bottom right, the mathematical matrix for the errors of reconstruction. And we can complete this mathematical matrix with a more physics-based diagnostic. For example, the power spectrum of the vorticity. The idea of this diagnostic is that we can decompose a flow by the power spectrum of this vorticity. And there is very nice theories associated to this. But the idea is that the more close we are to the dots, like black points, which is ERA 5, the better we are physically. And we can see that our model, which is a red line, is a bit closer to the green line, which is another machine learning model. Especially, we can see that the machine learning model is presenting two minimum, like under the our ground truth, which are telling that it's a bit smoother. And when sometimes a model is a bit smoother, it is presenting some nice mathematical 10 minutes already? Oh my God. Okay. Then I'm going to quickly show like the second part, which is the prediction. We are going to use an architecture, like state-of-the-art architecture developed by NVIDIA, but we're going to modify a bit. In their case, they inputted like just an image. In our case, we are going to give us an input sequence of image. So now I'm going to show the results. So for the end-to-end model, from the observation to the forecast, I choose as a test case the Kirk storm, which was an extratropical transition in 2024, which was formed near Cape Verde and came across Europe. On the left, the ERA 5 analysis. On the right, our forecast model, 1 hour forecast. And on the background, the satellite images. I put in the satellite images because at the end of the day, ERA 5 is just a model, so it's nice to have a vision of the real flow which is happening. And we can see that globally we're capturing well most of the structure, like this on the near the US, this very south branch coming from subtropic of jets. Even on the north, like this flow coming from Greenland, which is very north and tight. And yeah. To conclude, we developed like an end-to-end methodology from observation to forecast. Our starting point was observation, not as most of the machine learning model developed nowadays. And the method must be extended to the lower atmosphere, where wind shear is dangerous. I think I can pass for the main achievement, paper and preparation, conferences, etc. And I think if you have any question, I can reply, and I will let you with a nice video of a wind shear that I captured 5 years ago in Toulouse. Thanks.